Okay, so here, this first one we have, a buffer is prepared using 0.6 moles of acetic acid and 2 moles of sodium acetate, okay, to enough water to make 1 liter of solution. All right, so we have a weak acid and its conjugate base. That's going to make a buffer. Okay, that's going to make a buffer. So if we think about it here, we have a rice table. Now, I'm going to show you, this first one is like the really, really long method of doing it. And then I'm going to show you a shortcut to it as well. Okay, so here we can use a rice table. So we start with our 0.6 moles, of our acetic acid. We don't have to worry about H2O, but we write in the equation just because it just makes it look nicer. Okay, and then we're going to create some H3O plus, or hydronium ion, and our acetate ion. Now, sodium acetate is 100% soluble in water, so it's going to all dissociate and break into that acetate ion. Okay, so we're going to start with 0.6 moles of this, that's our initial, and none of this, and 2 moles of this. Okay, now we're going to assume that all this weak acid is going to turn into the acetate ion. Okay, so we're going to get minus X and plus X over here. So we get 0.6 minus X, X, and 2 plus X for our equilibrium concentrations. Okay, now when we set up our Ka statement here, we have Ka equals H3O plus times the acetate ion over the acetic acid. Okay, and then when we plug in our numbers, we get X, 2 plus X, 0.6 minus X. And then as far as we're concerned, we can use that 5% rule. We can assume that the amount of dissociation going one way or the other is going to be minimal. So these X's are going to be very small. Okay, we're going to ignore those, and the X's are going to be very small. And then what we're going to do is we're going to solve for X here, because that's what we want to find, right? The H3O plus concentration. So we're going to solve for X by doing the 0.6 over 0.2 to get rid of these two. That cancels with that, that cancels with that. Multiply that on one side, we got to do it to the other. So Ka times the 0.6 over 0.2 equals H3O plus. And we'll get H3O plus to be this. And now the pH is 5.3. Okay, so that's kind of the proof. That's the proof. Because when we do these problems, you don't have to do all that. Okay, you do not have to do all that. Okay, there's 2 equations we can use, and it's totally up to you which one you want to use. Okay. When we have a buffer solution, we have 2 equations we can use. Okay. The one that I gave you in the notes and that the handout thing, it says that if we take the Ka and we multiply the concentration of the acid over the concentration of the base, we should get the H3O plus concentration. And that's exactly what we did here. Okay, if you look at it here, I have Ka equals the base over the acid. And then in order to solve for this, we do the acid, this 0.6 is the acid. And this 2 is the concentration of the base. Okay, so we could have skipped all this stuff here. We could have skipped everything and just gone right to this equation right here. Okay, so this is one equation we can use. The other one we can use is the Henderson-Hasselbalch equation, where we actually we go all the way to pH. So pH equals pKa. Is it plus or minus? Oh, I just forget. Let me look it up. It's minus? That's plus. Okay, plus. Plus the log of the acid over the base. That's called the Henderson-Hasselbalch equation. My teacher used to call it the David Hasselhoff equation. But I personally, I think this is better. Easier to remember. And then we know pH is just the log of this. So I think it's easier. These are the same equation. This one and this, they're the same equation. It's just that we have logs in this one. The log of everything is taken. Whereas this one, we didn't do the log just yet. Because if you remember, log of one thing times the other thing is like adding them together. This is the log of the Ka plus log of this. It's just when you add them, you multiply, it's the same thing. So I prefer this one. Okay, and then if you have Kb, so if you have the weak base with its conjugate acid and you have a Kb value, it's very similar. It's just the opposite, base over acid equals OH minus. So these two equations. But again, this, I just wanted to do this to show you where this comes from. This is all of the work. This is the shortcut. You just say, all right, I know all of these x's are going to cancel out, and I'm just going to wind up with this in the end. So if you forget this, for whatever reason, if you forget this, do the Ka statement. Do the Ka, you'll get the same answer. Do the Ka, do the equilibrium, you'll get this work in the end. Okay, same thing. If you forget this, do the work. Do the rice table. Do the rice table. Doesn't really take that much more time. Just kind of maybe like, I guess it kind of takes like twice the amount of time, but it's not a lot of time. Okay. So next one, number 2, is very similar. This one we have, what is the pH of a solution prepared by dissolving 15 grams of sodium bicarbonate and 15 grams of sodium carbonate in enough water to make 0.25 liters of solution. So first I had to find the concentration of each of these. So I did the grams to moles, and then divided by the molarity. Now, in reality, this doesn't really matter in the end. This 250 liters of solution or 250 milliliters of solution doesn't really matter because they'll cancel out. When you do this divided by this, they actually cancel each other out. So it doesn't really matter how much water you have. The pH of the solution, regardless, will always be the same. So it doesn't really matter that much at all, actually. But I did it anyway. I it makes me feel safe. I know I get the right answer. Okay, so I did concentration of the acid, concentration of the base, right? I showed all the work here, but again, you don't need to show the work if you don't want to. You can always do the equation that is given here. This Ka acid over base, right? So Ka acid over base. That's what's right here. Concentration of the acid over the concentration of base times the Ka gives you the H3O plus concentration. I showed all the work if you want to see it. So then we get the H3O plus to be that, the pH to be that. So just be aware, even if you have a Ka value they say it's an acid, the solution might not always be acidic, right? Might not always be acidic. This is a basic solution. Just be aware of that. Okay, number 3. Any questions so far? 1 and 2. Not too bad, right? Not too bad. They get harder. Not too much harder today, though. Okay, here we have 4.13 grams of, I don't know what that is, sodium NaC9H7O4. Not sure what to call that. Anyone know the name of that? I don't know. And then is added to 250 milliliters of the acid of that conjugate base. What is the pH of the buffer? So this one kind of, the 250 milliliters does matter because we have a molarity here. I mean, we got to find the concentration of this. So 4.13 grams divided by its molar mass, we get that many moles, divided by the number of liters, we get that molarity. Okay? And then again, I showed the work, but you didn't need to. You could just do that. Ka equals acid over base. Or Ka times acid over base equals H3O plus. That's what I meant. Ka, acid over base, and you'll get the H3O plus concentration. That's it, and the pH is that. Pretty simple. Pretty simple, right? 1 through 3, not too bad. Okay, number 4 and 5 are a little bit of an introduction to creating a buffer from a weak acid and a strong base. But in this case, we even threw a little bit more of a little wrench in it, and we have some of the weak bases, the weak acids conjugate base. Okay, so we have this. We have 0.2 molar HC2H3O2 and 0.15 molar NaC2H3O2. Then we add, now this is the kink in it, we add the 0.005 moles of NaOH. So the first thing we need to think about is this NaOH is going to react with the weak acid, this HC2H3O2, the acetic acid. It's going to react with that, it's going to neutralize it, and it's going to form the acetate ion. So first thing we got to figure out is, okay, how much acetic acid do we have? How much acetate ion do we have in the original solution? So we did the molarity times the liters. Molarity times liters, we get number of moles of acetic acid, number of moles of acetate. Okay. Then we know that if we add 0.05 moles of NaOH, that's going to react with the acetic acid and subtract. It's a 1-to-1 ratio. So we're going to lose that many moles of acetic acid. So I subtracted it. So 0.025 moles of this minus 0.005 moles of the NaOH. And that's, when we do that, we get 0.02 moles of the weak acid left over. Then in order to get the concentration, I divide by the 0.125. I'm going to assume that This does not add, it doesn't say anything about the volume changing, so I'm going to just assume that the volume stays the same. I know it doesn't, but I'm just going to assume it stays the same because they didn't give me enough information to figure out what the volume changes. So we're just going to keep it the same. Okay, so that will give me the concentration of acetic acid left over. Okay, and now everything that reacts with this acetic acid will turn into the acetate ion. So we're actually adding to the acetate. So we take the original amount of the acetate, we add the 0.005 to it, and we're going to get how much acetate ion we have after the reaction. Divided by the number of liters, we'll get the concentration of acetate ion. Okay, so now we have the new acetic acid and new acetate ion concentrations, and we can plug that in using this equation again, Ka over concentration of acid over concentration of base. That's basically what I did here. I didn't even really show all the work for that, but you know, you're getting rid of these here and here, just multiplying 0.19 over 0.16 on both sides, and you'll get the pH to be 4.7. Okay, so that when we're adding the acid's going to react, we're adding the base is going to react with the acid, so the acid is going to be subtracted, and the acetate ion is going to be added. Okay, we can also have the opposite happen, and that's what number 5 is showing. So number 5 is showing the opposite. So if we have a buffer with the weak acid, so NH4 is the weak acid, and then we have a conjugate base of NH3, so that's conjugate base, so weak acid. Then if we add acid to it, what will happen? So if we add acid to it, this acid is going to react with the weak base, or the conjugate base, I should say, the conjugate base. So it's going to be the opposite. So this one, they gave us number of moles of this and moles of that, so we didn't actually have to figure out how many moles of each. So I did 0.02 plus the 0.015 because we're adding the acid, so we're going to get more acid. And then the base minus the amount of strong acid we added. And we get how much we wind up with. Then we divide by the number of liters of solution. We didn't actually really need to do that, but I did it anyway, just because it makes me feel more comfortable. If you did it with it or without it, you'll get the same answer. And then again, I showed the work here, but you don't need to. You could just have done the Ka times concentration of acid over concentration of base equals H3O plus. You get H3O plus to be this, and you get pH of that. Okay? Okay, that's really it. Those 5 problems. Okay? You're going to do the same thing for the other 5. So those are the 5 examples. They're exactly the same as the practice problems, except I changed numbers. Just get used to doing this. They do get more difficult. Oftentimes, what they're going to ask you, and we'll get to this probably a little bit tomorrow, is what's the buffering capacity? So how much HCl can you add, or how much NaOH can you add before the buffer is totally kaput? Okay, and basically it would just be that many moles. So if you added 0.2 moles, or actually, sorry, it would be this one, 0.075. If you add 0.075 moles of HCl, then the buffer would be kaput. There wouldn't be a buffer anymore. Okay. A lot of times the questions on the AP exam will ask you, what is the pH to start with? If we add this much HCl, what's the new pH? If we add this much, what's the pH now? If we add this much more, what's the pH now? And usually it's different points. So first is it's within the buffer. The second point is like at the buffering capacity. And then the third point is above the buffering capacity. So once it becomes totally just HCl in solution. Okay. And we'll look at some of those types of questions probably tomorrow. Okay. But try these ones. If you want to work through the rice tables just to like get the feel for it and see what it's like, you can. Otherwise, feel free to just skip right to the this Ka equation if you want to. I like working, even when I haven't done these problems in a while, I like working through one or two rice tables just to remind myself of where this equation comes from. Where does this equation come from? It helps me remember, helps me feel better about it, makes me feel more confident in my calculations. Okay, but totally up to you. If you want to go right to the equation, that's fine with me. Okay, and that's it. Really 5 simple problems. Take your time, make sure you get it, understand it. Okay, and that's it. I'll see you guys tomorrow. I'll be around here if you have any questions, okay? Bye, guys.